Thank you very much for this kind invitation. It's a pleasure to be giving a talk here. I wish I could have made it offline, because I wanted to travel to Bangalore, but unfortunately it's not possible at this moment. Let me begin. Today I will talk about some special cases of the Abhyankar-Sathaye conjecture. So when I say special cases, that means the conjecture is still an open problem. So some cases have been solved and we will be discussing those cases. So let me begin with a picture of Professor Sriram S. Abhyankar, who was a pioneer in this field. And he, in fact, had written a poem on polynomials and power series, May They Forever Rule the World. So if you're interested, you can read this poem. So he was, can be taken as a founder of this area of affine algebraic geometry in which I am working with. And Abhyankar-Sathaye's conjecture is one of this problem in this area. So let me begin with some notations. Throughout my talk, K will denote a field. For any ring A and R, A equal to R square bracket n, this would mean that A is isomorphic to a polynomial ring in n indeterminants over R for some algebraically independent elements x1, x2, xn over A. A polynomial f is called a coordinate, or sometimes I call it a variable, if there exists f2, f3, fn such that f is like one of your x's, like f is up to an automorphism, you can change f to x1. So if A equal to Rf, f2 up to fn, that is f is a coordinate. So this is the definition. For example, let me do it in two variables. For any polynomial phi, psi, and eta, the following are coordinates. So for instance, from x and y, so there are a pair of coordinate in Rx, y. You can change it to x to y plus phi x, change y to y plus phi x. Now you can apply another automorphism and change x to x plus a polynomial in y plus phi x, and then y remains intact. So each step you can see it is an automorphism. So you can go back to your x and y. So all these are coordinates. You can go a step further and keep your x fixed, the image of this fix, and change y plus phi x to y plus phi x and a polynomial in x plus y plus phi x. So if we keep on doing this, it will be clear that as more and more we progress, these coordinates are getting complicated. So initially what was very simple looking x and y, after some 3-4 steps, it has become a highly complicated polynomial, and then it becomes a difficult problem. In fact, it is an open problem to determine whether a given polynomial is a coordinate. So that is where the theme of this talk is. Often it is very hard to determine whether a polynomial is a coordinate, and one of the obvious necessary condition is that if f is a coordinate, then if you go modulo f, then the result will be a polynomial ring in one variable. So actually, see for instance, f is equal to x, then Rxy mod x is R1. The theme of this talk is whether the converse is necessarily true. Let me begin with a famous theorem. This is the first version proved by Abhyankar and Moh. For any field of characteristic 0, if f and g are two polynomials in one variable, such that you can obtain W. So W is the f and g are polynomial in W. So if you, so that you can obtain W from f and g, then the following is true, that either the W degree of f will divide the W degree of g, or the W degree of g will divide the W degree of. So what is the importance of this result? As a consequence, we get this the epimorphism theorem, which was also proved by Suzuki over the field of complex numbers, that if f is a polynomial which defines a line, that is kz t mod f is k1, then f is a coordinate. So this is the Abhyankar-Moh Suzuki, which is also known as the epimorphism theorem. So the epimorphism problem for hyperplanes can be posed as, so suppose f is a polynomial in x1 up to xn, and if it defines a affine n minus 1 plane, that is k x1 x2 xm mod f is kn minus 1, whether f is a coordinate. So we have seen that for n equal to 2, the answer is yes. This was put by Abhyankar-Moh Suzuki result in characteristic 0. However, in positive characteristic, the answer is no, and it was known much before, around by this examples of Segre around 1957. So here comes a definition. A polynomial f will be called a non-trivial line if defines a line that is kzt mod f is k1, but f is not a coordinate. So we have seen this Segre-Nagata examples that over a field of characteristic P positive, if you consider this small f, which is a polynomial in 2 variable, then f is a non-trivial line in KZ. So the epimorphism theorem says that in characteristic 0, there does not exist any non-trivial line. However, in positive characteristic, there are non-trivial lines. The Abhyankar-Sathaye conjecture asserts that in over a field of characteristic 0, any hyperplane, that is if f defines an n minus 1 plane, then f must be a coordinate. So, and we have seen this result for n equal to 2. However, this problem is still an open problem for any integer n greater than or equal to 3, and no counterexample is known till date. Some special cases have been taken care of. Say, for example, the first special case was taken by Sathaye in characteristic 0 and Russell in arbitrary characteristic. He considered a polynomial g which is linear in one of the coordinates, say linear in y, and a and b be arbitrary polynomial in xz. Suppose this g defines a plane. Then they proved, both of them proved independently, that there exists an coordinate x1 in xz such that the coefficient of y is actually a polynomial in that x1, and g is a coordinate along with x1 in xyz. So in this way, they have completely settled the linear plane conjecture, this Abhyankar-Sathaye conjecture, for this special case, which is the linear plane. Some special cases were also taken by David Wright. So David Wright, he proved that over an algebraically closed field of positive characteristic, he considered of any characteristic 0 and any plane, he considered polynomials of this type, where you have z to the power n and there is arbitrary coefficient from xy and some constant from xy. Suppose this g defines a plane, and this p must not divide n, because if p divides n, there is a counterexample. So they proved that there exists an x1 such that which is a coordinate along with this b. So this b itself becomes a coordinate along with x1, and this a is a polynomial in x1. In particular, they showed that g will be a coordinate along with z and this x1 which they found. So David Wright proved this result for algebraically closed field, and in 2011, Prosenjit Das and Amartya Kumar Datta, both of them proved this result for any field, means arbitrary field of characteristic p greater than or equal to 0. So this I will come later, that why this generalization to any field was important. Now let me state a few more results in this direction. So this result was due to Russell and Sathaye. He also considered, they considered this polynomial in xyz, but with one hypothesis, that these coefficients an minus 1 and a1, these coefficients of have a GCD which is not a constant. So under this hypothesis, they proved that you can find a coordinate x1 in xy such that the GCD is a polynomial in x1 and G is a coordinate. So so this were of certain kind of result. In a different direction, Diliman, he proved over a field of complex number, he proved that if the almost general fibers are defines an affine plane, then G must be a coordinate. So, and you can see that after 1979, this is the next result, and till date there is no further development. Now I come to the generalized epimorphism problem. So what is that? So let R be an integral domain of characteristic 0, and suppose phi is an epimorphism from R algebra epimorphism from a polynomial ring in n variable to a polynomial ring in n-1 variable, and I be the kernel of phi. So this epimorphism theorem for field was when R is a field K. Now there are two questions which can be asked. First of all, is I necessarily a principal ideal? Note that if R is a field K, then I is an height 1 primordial and hence principal. Because height 1 primordial and this ring is a UFD, will turn out to be a UFD if R is a field. So then this question does not make sense. This question is not so important when R is a field. But for arbitrary integral domain, this is a very well valid question and it's important. And the next question is, suppose you assume that the kernel is principal, is generated by one polynomial f, then is that f necessarily a coordinate? Both of these questions were answered, can be dealt or answered for only those n and f for which the field case has already been settled. So this generalized epimorphism problem is altogether a different game, because here you first need to know the field case, and then what we do is that we use the techniques of affine fibrations, which I will come later. So this answer to the question 1 was answered by Professor Bhattwardekar. He proved that when I is a principal ideal, whenever R is Noetherian semi-normal domain. And further, if R is not a semi-normal domain, then I need not be principal. So in his paper, he actually answered question 1 completely. He moved further for the 2 variable case where this result has already been known in the field case. Now if f defines a line, this I should say not an affine. So Rxy mod f is R1, whether f is a coordinate. So this was answered for an unique factorization domain, or in particular for a more precisely for a locally Noetherian rings, which was answered by Russell and Sathaye. And later Bhattwardekar sir proved that you need to assume only if the result is true, if R contains the field of rational numbers. And also if R is a Noetherian semi-normal domain. So further, the answer is no if R neither contains Q or R is not semi-normal. This was answered recently by Asanuma and Professor Datta. As a consequence, I should not say it is a consequence, it's actually a theorem. It doesn't follow directly from this epimorphism theorem of Bhattwardekar, that for an integral domain, if it contains the field of rational numbers, or if it is Noetherian semi-normal domain, then f is, and suppose f defines a plane, and you can find an element u in Rxy such that u is a coordinate in B, then your f is a coordinate along with u. So this is slightly non-trivial result, but you can see the importance of this result. And this is true in particular if you replace R by any k, all these hypotheses k, field k of characteristic 0, all these hypotheses are going to be satisfied. So I am saying this Abhyankar-Sathaye conjecture is true if you can find an element u in Rxy which becomes a coordinate in B. So, yeah. So here's a picture of Professor Datta, Professor Bhatwadekar, and Avinash-Sathaye. This is the Abhyankar-Sathaye's conjecture I'm referring to. And they have done this work on this linear planes, generalization of the linear planes of the Russell-Sathaye result. So recall that for the field case, this was proved by Russell and Sathaye that whenever f is a linear polynomial, then we have that f is a coordinate. There is a typo, it should be f. I made a mistake here. Now, what Bhatwadekar and Datta did, they considered a discrete valuation ring, replace R by a discrete valuation ring, and if pi is a uniformizing parameter, capital K is the field of fractions of R, and small k is the residue field of R. So they proved this result that if f defines a plane where f is this special type, then you can find an x naught in Rxy such that the coefficient of z is a polynomial in Rx naught. So you can see the similarity between the field case and the ring case. However, this result is not complete. You need to assume that if either pi does not divide A, then f is a coordinate, or if the transcendence degree of x naught bar, so x naught and f, the bar denotes the images in the residue field. If the transcendence degree is 2, then f is a coordinate. So you may be wondering that why this is such a complicated conditions are taken care of, because I will explicitly give you an example, which is an open problem for more than 30 years now, about an example of an f which does not satisfy any of this condition, and it is not known whether f is a coordinate. Explicit example. So, but that example is connected to another problem known as the affine fibration problem. So it is a bit technical. So for any ring R and a prime ideal P of R and A and R algebra, let Kp denotes the field of fractions of the integral domain R mod P, and A tensor Kp denotes the fiber ring of A at the point P. Then a ring A is called an AN fibration over R if A is flat over R, A is finitely generated over R, and all the fiber rings of A over R is a polynomial ring in n variable. An open problem asked by Dolgachov and Westfeller was for a regular local ring of dimension D, whether any AN fibration is necessarily a polynomial ring. So this is still an open problem, and few special cases have been answered. So the first case was the case A1 fibration. This problem has been completely answered by Kambayashi and Miyanishi. Later, Professor Datta proved that you can assume the fiber condition only on the codimension 1 fibers. So unlike the A1 fibration case, which was proved for a ring of any dimension, for n equal to 2, this is highly non-trivial result by Sathaye that if R contains the field of rationals, then the answer is yes. However, Professor Asanuma gave an example that if R does not contain the field of rational numbers, then the answer is no. Sometime I have proved that for any dimension, any regular local ring of any dimension, A2 fibration problem does not have an affirmative answer if R does not contain the field of rational numbers. And it is still an open problem if R contains the field of rational numbers and n equal to 2 and d equal to 2. So field of fractions and quotient rings are probably the same ring, right? Quotient field means what? There is a question by...
no, you see, in general, quotient rings can be more rather than the classical quotients.
Yeah, so the fibration problem is actually the all quotient rings, but for a discrete valuation ring, there is only one fiber. So that I have written down explicitly.
Okay, thank you. Thank you.
Okay. So, and till now, the best known result is due to Asian-Ochian, who proved that any AN fibration over a regular local ring is a stably polynomial. So after adjoining few more variables, it becomes a polynomial ring. So as of now, this problem does not seem to be quickly answered. Now this comes the example of Bhatwadekar and Datta. So here this A is a polynomial ring in 4 variable and F is this a spatial polynomial. So look at this spatial polynomial, it is linear in Z. So Z appears only here and rest of it is X, Y, Z. And T actually is my uniformizing parameter for the discrete valuation ring which I was talking about. So then it can be shown that F defines a affine 3 space. In fact, it's A mod F is a polynomial ring over CT. In further, it is a stably polynomial ring. That is, after adjoining one more variable, it becomes a polynomial ring. Inverting F, again, A is a polynomial ring over CTF. In particular, it is an A2 fibration over the subring B, CTF. And it is an open problem whether A is a polynomial ring over B, at least whether A is a polynomial ring over the polynomial F, CF. If the answer is no, it is a counterexample to the 3 famous problems: the Abhyankar-Sathaye epimorphism problem for the n equal to 4 case, A2 fibration problem for C2, and cancellation problem over C1. Now, I also come to the generalization of the David Wright result for the ring case. So here, recall this result of David Wright, and for arbitrary field of characteristic p greater than equal to 0 and p not dividing n is this integer, they proved this result. So similar result had also been proved by Datta and Das in 2011, that if R is an integral domain containing a field of characteristic P, then if F defines a plane where F is of this special type, and suppose R contains either the field of rational numbers or R is semi-normal, then Rxyz is a polynomial ring over R, F, and Z. So Z becomes a coordinate. So this case, generalization of David Wright result has been completely answered for arbitrary integral domain. However, as we have seen, for the linear plane, that n equal to 1 case is highly non-trivial and some partial results are known. Now, I come to the result of mine, which I proved. So here I consider a polynomial G of this type, which is a linear polynomial in Y with coefficients x to the power r, and if small f denotes the projection along the line x equal to 0, and suppose A is this ring and R is an integer greater than 1, then I proved the equivalence of the following statements. So this ring A is a polynomial ring if and only if it is a polynomial ring over the subring Kx, where small x is the image of capital X in A. Moreover, all these conditions are equivalent to say that small f is a coordinate Kzt. And if any of this condition is satisfied, then G is a coordinate in XYZT. And if G is a coordinate along with X. So this result of mine, it proves that this ring A is a polynomial ring, then G is a coordinate along with X. So this proves a partial case of the Abhyankar-Sathaye conjecture, which also extends partially the Sathaye-Russell theorem for the case n equal to 4. Further, this result that A is a polynomial ring, if and only if A is a polynomial ring over the subring Kx, this says that answers the result of that. This is a very special case of showing that an example of asanuma is not going to be a polynomial ring. And for any non-trivial A2 fibration, so A will define a non-trivial A2 fibration if and only F0ZT is a non-trivial line. So we know that a non-trivial line exists in positive characteristic. So we also get a counter example to the A2 fibration problem over a discrete valuation. Recall that there is an example due to Russell, also known as Russell-Chorus threefold, over the field of complex number. This is very similar to my example, and it was an open problem for some time whether A is a polynomial ring. And it was answered by Makal-Limanov that no, using some techniques of GA actions, which we have also used. Now it follows very easily from my theorem that this polynomial A is not a polynomial ring. This ring A is not a polynomial ring because Z square plus T cube cannot be a coordinate in Z. It had been an open problem whether A is a polynomial ring, because if the answer is yes, then it would have been a counterexample to the Abhyankar-Sathaye conjecture and also to the linearization conjecture. Now in fact, what I had proved an equivalence of 13 statements, which I will skip because there is no time. And also this result, because their generalization I'm going to talk in the next slides. These are some of the results which I proved earlier. I also proved, see, now you consider a polynomial in m plus 3 variable and a ring of dimension m plus 2 of this type. So we have shown that if small f is a line, then this ring A is a polynomial, is a stably polynomial ring. So, and I would be showing that if f is a non-trivial line, then A is not a polynomial ring, and hence this kind of rings gives counterexample to the cancellation problem in higher dimension. Let me now come to the more general result. So take a field of any characteristic. This was proved jointly with Pornoshri Ghosh. So, and G be a polynomial of this type is a special polynomial that fzt plus this, and each integer ri is greater than 1. Then we have proved the similar statements in higher dimension, that this ring A is a polynomial ring in m plus 2 variable if and only if small f is a coordinate, and if and only if this G is a coordinate in B. So note that this gives a special case of the Abhyankar-Sathaye conjecture, that if A is a polynomial ring, then G is a coordinate, and we proved that G is a coordinate along with x1, x2, xm. Further, the question whether G, this polynomial G, is a coordinate in B or not, reduces to the question whether small f is a coordinate in ZT, which is just 2 variables. And this we can answer, or we can determine whether a polynomial in 2 variable is a coordinate or not. So, and in fact, we have proved a much more general, proving equivalence of 8 more statements. And further, we also proved that if you note that this ring have parameters R1, R2, Rm and F, which is a non-trivial line, then we proved that 2 such rings are isomorphic if and only if R1, R2, Rm is equal to S1, S2, Sm up to some permutation. And this F and G are equivalent to each other, are associate of each other. Thus, as we know that if F is a non-trivial line, then these rings are stably polynomial ring. And by the previous result, it follows that if F is a non-trivial line, this ring A cannot be a polynomial ring. Hence, over a field of a positive characteristic, there is an infinite family of non-isomorphic rings, which are all stably isomorphic to the polynomial. For techniques to prove this involves GA actions, which unfortunately I have to skip, and an invariant related to GA actions, namely the Duxon invariant and Makalimanov invariant, which can be defined using GA actions. So we proved that for this ring B and this polynomial G, arbitrary polynomial of this type, we have proved an equivalence of 13 statements, which apparently look different, and which involves the cancellation problem, the epimorphism problem, and also the fibration problem. So these 5 statements I have already displayed. Then the next 4 statements involves an invariant, the Duxon invariant of the ring A. If the Duxon invariant of the ring A is equal to A, then this ring A is a polynomial ring if and only if it satisfies any of this condition, that A is a stably polynomial ring, or if it is an A2 fibration, or small f is a line, or the best is to minimum is to assume is that A is a unique factorization domain with the units of A being trivial. And similar statements using the Makaliman invariant have been proved. So I stop here. I hope I have not overshot it.
Yeah, thank you for a nice talk. So there are some questions in the chat.
Sure.
It says that, is there a basic difference in coordinates which involve only some of the variables and those that involve all?
Yeah, sometimes we can use sort of induction if it involves fewer variables. But as we see that for n equal to 2, identifying a coordinate can be done because we have a knowledge of the automorphism group of K, Z, T. In 2 variables, we know the automorphism group over a field K. However, moment it is n equal to 3 or more, the automorphism group of the polynomial ring is highly wild. It's not known, and classifying them is an open problem. So unless we know the automorphism group, it becomes difficult to find whether something is a coordinate. So here the problem lies.
The second question is, does irreducibility play any role?
Irreducibility of what?
The example is Z2 plus T3 is irreducible. So
yeah, it is irreducible because that is anyway needed, because for the ring A to be an integral domain, for any ring A to be an unique factorization domain, you need Z square plus T cube to be irreducible. So it was known that the ring A, which display that ring. Because of lack of time, I have not gone in much detail of that example. So this example is, by the way, a highly popular example known as a Russell cubic. And this ring A was known to be a unique factorization domain. It is a regular ring. In fact, it was known to be diffeomorphic to R6 in the Euclidean topology. And recently it has been proved by Dubulers and Fuzzle that this ring A is A1 contractible. So A1 contractibility is another notion of topology in a algebraic geometric sense. So it has been proved that these rings are A1 contractible. So even then, this ring A is not a polynomial ring, and now it is an open problem whether this ring A is a stably polynomial ring. So after adjoining one more variable, it's not known whether A1 is a C4 or not. Because if it turns out that A1 equal to C4, then we will have a counterexample to the Zariski cancellation problem for the characteristic 0, in fact, for complex numbers. So which will be again a very difficult and this highly important problem.
Are there any questions?
Thank you. Thank you. You see, I use we have these multivariable polynomials for studying quantum entanglement with other people. So I find your talk very useful and very interesting. Thank you.
Maybe a very naive question, Neena.
Yes.
Supposing you have identified an F to be a coordinate in a certain ring, is there any other possibility of a coordinate? I mean, is it uniquely defined?
Uniquely defined in what sense?
I mean, of course, if you see C, X, Y, Z, T mod G, G is going to be a coordinate, isn't it?
No. This G is actually, this A is not C3. So G is certainly not a coordinate.
Oh, I see in this case. But if there is a coordinate, it is that, I mean, the generator of that ideal, or like here.
Okay, here.
I don't know which page to go to. Yeah, supposing there was a coordinate, F is a coordinate. What I'm asking is, if F is a coordinate, is it possible to have another G of Z comma T also as a coordinate?
Another G of Z comma T.
Anyway, I can ask you later. I think I don't want to keep people.
No, Mrs. Maybe you can ask it more precisely. And so maybe what you are asking is that if G is a coordinate, then it means that G is a coordinate along with some more, you need 3 more variables like H, U and V for G to be a coordinate. Whether H, U, V are uniquely determined? Of course not.
Yeah.
So H, U and V will keep on changing. That is not uniquely determined.
Yeah, that's what I was trying to say. Yeah.
So that keeps on changing.
I see. Okay.
Even for 2 variables, it is easy to see. For X is a coordinate along with Y, but X is also a coordinate along with Y plus X square.
Exactly. Yeah.
That's not.
Okay. Got it. Thank you.
Are there more questions? If not, then let's thank the speaker again for a really nice talk.
Thank you.